Hello there, and welcome to Life Beyond Seen, where curiosity slows down, where science softens its voice, and where big questions are allowed to stretch out and breathe. Tonight's journey drifts far south, beyond familiar maps and frozen expectations, to a place that feels timeless and impossibly distant. Antarctica. Not the white continent we picture today, locked in ice and silence, but something far older, warmer, and far more alive than it has any right to be. A version of the world where seas rolled gently against green shores, where sunlight lingered for months at a time, and where the ocean was rich enough, vast enough, and productive enough to support one of the largest predators ever to live, the Megalodon. That idea alone feels slightly wrong at first, doesn't it? A colossal shark associated with warm coastal waters, palm-lined shores and sunlit seas, somehow connected to Antarctica, a place we associate with cold, darkness and emptiness. It sounds like a contradiction, like imagining a rainforest beneath a glacier or coral reefs growing under falling snow. And yet, the deeper scientists look into Earth's past, the more these contradictions begin to soften. The planet, it turns out, has never been particularly loyal to our expectations. Before we settle into that ancient ocean, take a small moment to notice where you are right now. Maybe you're listening late at night, the room dim, the rest of the world finally quiet. Or perhaps it's early morning, light just beginning to gather behind the curtains. Wherever you happen to be, whatever time it is in your part of the world, you're sharing this moment with countless others scattered across different hours, different climates, different seasons. There's something fitting about that, considering we're about to talk about oceans that once connected hemispheres, climates that blurred boundaries, and creatures that cared very little for the lines we draw on maps today. If you find this space calming, or if these slow explorations help you unwind after a long day, you're always welcome to like the video or subscribe. It helps this quiet corner of science reach others who might be craving something gentle and unhurried. And now, let's ease into the story itself, without rushing, without forcing conclusions, and without expecting the past to behave like the present. When we picture Antarctica today, we picture ice, endless, blinding white, a continent that seems more absence than presence. Little grows there, very little moves. The ocean surrounding it feels hostile, dark, and sharply cold, patrolled by creatures that have adapted to extremes. But this version of Antarctica is only a recent chapter in Earth's long and complicated history. For most of the planet's past, Antarctica was not frozen at all. It was not isolated. It was not even particularly cold. Hundreds of millions of years ago, Antarctica sat in a very different position, both geographically and climatically. It was part of larger supercontinents, connected to land masses that are now far away. Warm currents flowed freely around it. Seasonal darkness existed, yes, but it was paired with long, bright summers that fueled growth on land and in the sea. Rivers carried nutrients into shallow coastal waters. Forests grew where ice would later dominate, and beneath the surface of the surrounding oceans, life flourished in ways that are difficult to imagine from our modern vantage point. The ocean, after all, responds to temperature, nutrients, and circulation more than it responds to latitude. Warm water can exist at high latitudes if the planet's overall climate allows it, and for long stretches of Earth's history, it absolutely did. Greenhouse conditions dominated. Atmospheric carbon dioxide levels were far higher than they are today. Polar ice caps were either small or entirely absent. Sea levels were high, flooding continental shelves and creating vast, shallow marine environments that acted like biological factories. These kinds of seas are important. Shallow sunlit waters are where productivity explodes. Phytoplankton thrive. Zooplankton follow. Fish populations expand. Larger predators appear. Energy moves upward through the food web efficiently, creating systems capable of supporting enormous animals. This is not speculation. We see it today in places like productive upwelling zones and nutrient-rich continental shelves. Scale that up to a planet-wide warm period, and the results become extraordinary. This is where the idea of a giant like Megalodon begins to feel less strange. Megalodon did not appear in a vacuum. It emerged in oceans that were already capable of sustaining large, energy-hungry animals. Whales were diversifying. Marine mammals were spreading into new niches. Large prey existed, and where large prey thrives, large predators tend to follow. Size in the ocean is often an advantage. It allows long-distance travel, efficient energy use, and dominance over competitors. But size only works when the environment can support it. Ancient Antarctic seas were not barren. They were not quiet. They were busy, layered, and dynamic. Currents carried warmth from lower latitudes. Nutrients circulated through water columns. Seasonal cycles created pulses of productivity that echoed through the ecosystem. During long summers, sunlight fueled blooms that fed everything above them. During darker months, stored energy carried systems forward. Life adapted to these rhythms not by shrinking, but by specializing. It's also worth remembering that cold by itself does not eliminate abundance. Even today, some of the richest marine ecosystems on Earth exist in cold waters. The Southern Ocean supports massive krill populations that feed whales, seals, and seabirds. The key difference is not temperature alone, but structure. Ancient seas around Antarctica had extensive continental shelves before tectonic shifts and ice accumulation changed everything. Those shelves mattered. They created space. They created stability. They created opportunity. At its peak, Megalodon was an animal built for opportunity. Estimates suggest it could reach lengths of over 15 meters, possibly more. Its teeth were thick, serrated, and designed to process bone. Its bite force exceeded that of any living shark. Maintaining a body like that required constant access to energy-rich prey. This was not a creature that could survive on scarcity. It needed oceans that were generous, predictable, and expansive. And for a long time, Earth provided exactly that. As the planet drifted through warmer epochs, Antarctic waters were not isolated behind circumpolar currents yet. That isolation came later. Before that, warm currents from the north and south mixed freely. Heat moved efficiently around the globe. Marine species had broader ranges. Migration routes were long and uninterrupted. A giant predator could patrol vast territories without encountering the thermal barriers that would later fragment ecosystems. This matters because Megalodon was not a coastal ambush hunter in the narrow sense. It was likely a wide-ranging predator, capable of crossing oceans, following prey across basins, and exploiting seasonal abundance wherever it appeared. Ancient Antarctic seas would not have been a permanent home so much as part of a massive interconnected hunting ground. A place visited, used, and revisited as conditions allowed. The idea of Megalodon moving through southern waters also aligns with fossil evidence showing its teeth in a wide range of locations, including high latitudes. These findings suggest flexibility, not confinement. They suggest an animal that was comfortable wherever food was plentiful and competition manageable. In warm periods, that included regions we now consider extreme. What eventually ended this arrangement was not a sudden catastrophe, but a slow reorganization of the planet itself. Continents shifted. Antarctica drifted toward its current position. Ocean gateways closed. The circumpolar current formed, isolating southern waters and allowing ice to build. Productivity patterns changed. Marine mammals adapted or moved. Giants like Megalodon found their world narrowing, their energy budgets strained, their advantages less reliable. But before that long decline began, there was a stretch of deep time where the southern oceans were open, alive, and capable of sustaining predators that make modern sharks seem modest by comparison. Understanding that world requires letting go of modern assumptions and allowing the past to remain unfamiliar. And as we drift further into that unfamiliar ocean, it helps to remember that Antarctica was not always a land of ice. It was once something else entirely, and the sea surrounding it tells that story quietly, layer by layer, fossil by fossil, current by current, waiting for us to listen just a little longer. Long before Antarctica became shorthand for ice, emptiness, and extremes, it existed as something far more fluid, far more blue than white. To imagine it properly, it helps to forget modern maps for a moment and loosen the grip of familiar expectations. The continent we know today is a product of recent geological history, shaped by shifts that are still ongoing. For most of Earth's past, Antarctica was not sealed off at the bottom of the world. It was not locked into place by ice sheets kilometres thick. Instead, it occupied a changing position, drifting slowly through latitudes that allowed warmth, rainfall, rivers, and open seas to shape its edges. If you could stand at the shoreline of ancient Antarctica during one of these warm periods, the scene would feel surprisingly alive. The water would not sting with cold. It would roll in gently, carrying the smell of salt and plant matter, tinted green and blue by microscopic life flourishing just beneath the surface. The sky would stretch wide and bright during long summers, and during darker months, the sea would continue its quiet motion, unconcerned with human ideas of harshness or desolation. This was not a frozen frontier. It was a working ocean, busy and layered, doing what oceans have always done when given enough energy and space. The key to this forgotten blue world lies in plate tectonics. Antarctica did not always sit alone at the southern pole. It was once part of larger landmasses, stitched together with what are now South America, Africa, Australia, and India. These connections mattered. They allowed currents to flow differently, heat to circulate more evenly, and ecosystems to spread across vast, uninterrupted regions. Ocean gateways were open. Water moved freely around the globe, redistributing warmth and nutrients in ways that are impossible today. During these greenhouse periods, Earth's climate operated under a different balance. Carbon dioxide levels were higher, trapping more heat in the atmosphere. Ice caps were minimal or absent. Sea levels rose, flooding continental margins and creating shallow marine shelves that extended for hundreds of kilometres. These shelves were not empty expanses. They were some of the most productive environments on the planet. Sunlight reached the seafloor, nutrients accumulated, plankton bloomed in enormous numbers, forming the base of food webs that could support fish, reptiles, early marine mammals, and eventually large predatory sharks. Antarctica's surrounding seas were shaped by this abundance. Rivers carried sediment and organic material from the land into the ocean. Seasonal cycles stirred the water, mixing nutrients upward and sustaining productivity even during darker periods. Instead of being isolated, these seas were deeply connected to global circulation patterns. What happened in equatorial waters could influence conditions far to the south, and vice versa. Life did not recognize Antarctica as an endpoint. It was simply part of a continuous marine landscape. The land itself contributed to this richness. Fossil evidence shows that ancient Antarctica supported forests, wetlands, and diverse plant life. These ecosystems stabilized coastlines, slowed erosion, and fed organic material into nearby waters. Leaves, pollen, and woody debris became part of the marine nutrient cycle. In shallow bays and estuaries, life concentrated. These were nurseries for fish and invertebrates, places where young animals could grow before moving into deeper water. Such zones are crucial in modern oceans, and they were no less important in the past. Temperature gradients existed, of course. Even in warm periods, polar regions experienced cooler seasons and extended darkness. But these conditions did not prevent abundance, they shaped it. Organisms adapted to cycles of light and dark, periods of intense growth followed by slower phases. This rhythm created pulses of productivity that echoed upward through the food web. When plankton populations surged, everything that fed on them benefited. When prey animals thrived, predators followed. It is important to understand that warmth in ancient Antarctic seas did not mean uniform comfort or tropical calm. These waters could be dynamic, energetic, and sometimes violent. Storms swept across open oceans, currents shifted, upwelling zones brought cold, nutrient-rich water to the surface, fueling further growth. This mixing of water masses created complexity, and complexity supports diversity. The result was an ocean capable of sustaining large populations over long periods of time. In such an environment, size became viable. Large animals require stability. They need predictable access to food and space to move. Ancient Antarctic seas offered both. Migration routes extended across hemispheres. Seasonal abundance allowed predators to time their movements with prey availability. There were fewer barriers, fewer choke points, fewer regions cut off by temperature extremes or ice. For a large predator moving through these waters, the world was open. The idea of a giant shark existing within this system becomes less surprising when viewed this way. It was not surviving in isolation or against the odds. It was part of a broader ecological pattern where size and specialization were rewarded. The ocean did not constrain growth, it encouraged it. Another factor often overlooked is oxygen availability. Warmer oceans can hold less dissolved oxygen, but during certain periods circulation patterns compensated for this by constantly refreshing surface waters. High productivity also meant high oxygen generation near the surface. For large active predators this mattered. Sustained swimming requires oxygen. Efficient circulation supported that lifestyle, allowing animals to grow large without being limited by respiratory constraints. As Antarctica continued to drift southward, conditions slowly began to change. But this transition took millions of years. There was no single moment when warmth vanished and ice appeared overnight. Instead, the continent gradually crossed climatic thresholds. Currents shifted, gateways narrowed, heat transport weakened. Ice began to persist through summers, reflecting sunlight and reinforcing cooling trends. The once open system slowly closed in on itself. Before that closure, however, there was time. Time enough for ecosystems to expand, for giants to emerge, and for the ocean to experiment with scale. The fossil record preserves glimpses of this experimentation, not as complete narratives, but as scattered pieces that, when assembled, reveal a world far removed from modern Antarctica. What makes this forgotten blue world especially compelling is how unfamiliar it feels. We tend to think of places as having fixed identities. Antarctica equals ice, tropics equal warmth. But Earth does not respect those labels. It reshapes itself constantly, rearranging climates and environments in ways that feel counterintuitive only because our frame of reference is so narrow. The Antarctic seas that once supported immense predators did so not because they were exceptions, but because they followed the same ecological rules that govern oceans everywhere. Energy in, energy up, complexity builds, size follows. As we continue forward, it becomes clear that understanding how a giant like Megalodon could exist near Antarctica requires understanding not just the animal, but the ocean that carried it. That ocean was not marginal, it was central, it was not struggling, it was thriving. And its story does not begin with ice, but with movement, warmth, and a deep, persistent blue that filled the southern reaches of the world long before they froze. From this foundation, the next layer of the story begins to take shape. Because once Antarctica is understood as a living oceanic hub rather than a frozen outlier, the conditions that allowed immense predators to move through its waters start to feel less extraordinary and more inevitable. There was a time when the southern reaches of the planet were not defined by cold or scarcity, but by movement, growth, and an almost restless biological energy. The phrase, the South, did not mean isolation or extremity. It meant connection. It meant oceans that participated fully in global circulation, seas that exchanged heat and life with the rest of the planet, rather than hoarding cold behind walls of ice. During these long intervals of Earth's history, Antarctica and the waters surrounding it were not marginal environments. They were active, productive, and deeply involved in the planet's living systems. To understand how alive these southern oceans once were, it helps to picture Earth during a greenhouse phase. Global temperatures were higher, not by a small margin but by several degrees on average. There were no permanent polar ice caps. Snow could fall seasonally at high latitudes, but it did not accumulate year after year. Instead, it melted, fed rivers, and returned to the sea. Sea levels were dramatically higher, drowning coastlines and creating wide continental shelves that extended far beyond today's shorelines. These shallow seas absorbed sunlight efficiently and became engines of biological productivity. Warmth alone, however, does not guarantee abundance. What truly transformed the southern oceans was circulation. Without the Antarctic circumpolar current, which today isolates the continent thermally, warm currents from lower latitudes were free to travel south. These currents did not simply deliver heat. They delivered nutrients, larvae, genetic diversity and stability. They connected ecosystems across thousands of kilometers, allowing species to spread, adapt, and specialize over vast areas. In these conditions, phytoplankton thrived. Microscopic photosynthetic organisms multiplied in the sunlit surface waters, forming the base of the marine food web. Their populations rose and fell with the seasons, responding to light availability and nutrient mixing. During long southern summers, plankton blooms could stretch across enormous regions, turning the water a faint green as life multiplied by the trillions. These blooms fed zooplankton, which fed fish, which fed larger predators in a cascading chain of energy transfer. The southern oceans were not quiet during this time. They were full of motion. Storms mixed surface waters. Tides stirred coastal zones. Upwelling brought nutrient-rich deep water toward the surface. Rivers delivered sediments and organic matter from the land. Each of these processes reinforced the others, creating feedback loops that sustained productivity year after year. Where energy flows reliably, life tends to grow large. Fish diversified rapidly in these environments. Fossil evidence suggests a wide range of body sizes and ecological roles, from small schooling species to large, fast-swimming hunters. Marine reptiles had already demonstrated the viability of large ocean predators earlier in Earth's history, and mammals would later follow a similar path. The southern oceans were not merely populated. They were structured, layered, and competitive. Competition is an important piece of this story. In ecosystems where resources are abundant but not infinite, evolutionary pressure favours efficiency and dominance. Predators that can travel farther, hunt more effectively, and exploit larger prey gain an advantage. Over time, this can drive increases in body size, particularly in marine environments where buoyancy reduces the constraints imposed by gravity. Warm southern waters removed many of the limitations that would later return as the climate cooled. Seasonality played a crucial role. While warmth prevailed overall, the southern region still experienced pronounced light cycles. Months of extended daylight alternated with long periods of darkness. Rather than suppressing life, this pattern concentrated it. During light-rich months, productivity surged. During darker months, organisms relied on stored energy, migration, or slowed metabolism. This created predictable rhythms that predators could exploit. Large animals capable of travelling long distances could move with these cycles, following prey as conditions shifted. It is also important to recognise that warm does not mean uniform. Ancient southern seas included temperature gradients, fronts, and mixing zones. These boundaries often hosted especially high productivity, as nutrients and organisms from different water masses converged. Modern analogues include regions where warm and cold currents meet, such as the North Atlantic. These areas are among the richest fishing grounds on Earth. In the ancient South, similar dynamics would have existed on an even larger scale. Life on land contributed to this richness as well. Antarctica supported forests composed of species adapted to long daylight cycles and mild temperatures. These forests stabilized soils and moderated runoff, preventing excessive erosion while still delivering organic material to coastal waters. Leaf litter, pollen, and plant debris entered rivers and estuaries, feeding microbial communities and supporting complex food webs. Coastal seas became transition zones where terrestrial and marine productivity reinforced one another. As marine mammals began to emerge and diversify, the southern oceans offered opportunity. Early whales and their relatives experimented with size, feeding strategies, and migration. Some filtered plankton, others hunted fish or squid. Each new niche added complexity to the ecosystem. With complexity came resilience. With resilience came the capacity to support predators that required enormous amounts of energy. This is the context in which a giant like Megalodon makes sense. It was not an anomaly appearing in an otherwise limited system. It was a response to abundance. In warm, productive seas, where large prey animals existed in sufficient numbers, natural selection favoured predators capable of exploiting them efficiently. Size allowed longer fasting periods, broader hunting ranges, and dominance over competitors. The southern oceans during these warm intervals offered all the prerequisites for such a lifestyle. The idea that polar regions must be biologically poor is a modern misconception shaped by current conditions. In the past, the South was not defined by ice-driven scarcity. It was defined by circulation-driven abundance. The presence of warmth allowed metabolic rates that supported active lifestyles. The absence of permanent ice allowed continuous interaction between ocean and atmosphere. The result was an environment where life did not merely persist, but expanded. As the planet slowly cooled, this abundance did not disappear instantly. It diminished unevenly. Some regions cooled faster than others. Some currents weakened before others formed. Ecosystems adapted in stages. Large predators did not vanish overnight. They followed shifting conditions, retreating toward regions that still offered warmth and prey. For a long time, the South remained viable, even as the first signs of isolation began to appear. Understanding this warm, teeming southern world is essential because it reframes the entire question of how massive marine predators could exist near Antarctica. It was not a question of endurance against harshness. It was a matter of opportunity within a system that encouraged growth. The southern oceans were not testing grounds, they were proving grounds. As the story moves forward, the focus naturally shifts from warmth itself to what warmth enabled. It enabled dense food webs, it enabled large prey, and it enabled predators that pushed the upper limits of size and power. To see how those elements fit together, it becomes necessary to look more closely at the structure of these ancient oceans and the specific kinds of abundance they produced, because warmth was only the beginning of what made the South such fertile ground for giants. The idea that an ocean could feed something that seems impossible by modern standards depends entirely on how we define possibility. Today's oceans are productive, but they are also constrained. Ice caps lock away nutrients. Currents isolate regions. Human pressure reshapes food webs faster than they can recover. When we look at the present and project backward, it is easy to assume that the past must have been smaller, simpler, or less capable. In reality, many ancient oceans were operating under conditions that allowed them to support levels of biological abundance that feel almost excessive by comparison. These were not oceans scraping by on the edge of scarcity. They were oceans running at full capacity, fueled by heat, circulation, and time. Lots of time. One of the most important differences between ancient oceans and modern ones lies in nutrient availability. Nutrients are the currency of marine life. Nitrogen, phosphorus, iron, and trace elements determine how much phytoplankton can grow, and phytoplankton ultimately determines how much life the ocean can support. In many ancient periods, nutrient cycles were more generous. Continental erosion delivered steady streams of minerals into the sea. Volcanic activity added iron-rich material to the atmosphere and surface waters. Shallow seas allowed nutrients to remain accessible instead of sinking irretrievably into the deep ocean. These factors combined to keep primary productivity high over enormous areas. Instead of isolated pockets of abundance separated by vast nutrient-poor deserts, ancient oceans often featured wide belts of sustained productivity. This mattered enormously for animals higher up the food chain. Large predators cannot survive on sporadic success. They require systems that deliver energy reliably, season after season, generation after generation. Another key factor was the structure of ancient continental shelves. During warm periods with high sea levels, continental shelves expanded dramatically. These shallow regions are where sunlight penetrates easily and where nutrients are constantly recycled. Today, continental shelves make up a small fraction of the ocean's area, but account for a disproportionate share of its productivity. In the past, those shelves were broader, deeper, and more continuous. They formed massive platforms for life, stretching along coastlines that no longer exist. In the southern hemisphere, these shelves surrounded Antarctica when it was not icebound. Instead of sheer drop-offs into cold, dark water, the continent was fringed by gradual slopes and submerged plains. These environments fostered dense populations of fish and invertebrates, which in turn supported larger predators. The ocean did not abruptly transition from life-rich to life-poor. It graded smoothly, allowing food webs to build complexity without interruption. Complexity is essential for sustaining giants. Simple food webs collapse easily. Complex ones redistribute energy efficiently. In ancient oceans, multiple prey species filled overlapping roles. If one population dipped temporarily, others could fill the gap. This redundancy stabilized energy flow. For a predator like Megalodon, that meant fewer catastrophic shortages and more opportunities to hunt large prey consistently. Large prey is the next critical piece. An animal the size of Megalodon could not subsist on small fish alone. It required calorie-dense targets, animals rich in fat and muscle. Ancient oceans provided exactly that. Early whales, large fish, and other marine vertebrates evolved during periods of high productivity. Some of these animals were themselves experimental forms, trying out body plans and sizes that would later disappear. The ocean was testing limits, and many of those tests involved growing bigger. Whales, in particular, transformed marine ecosystems. As they diversified, they introduced large, slow-moving sources of energy into the system. Even fast-swimming species had predictable behaviours tied to migration and breeding. These patterns created opportunities for predators capable of exploiting them. The presence of large prey does not guarantee the emergence of large predators, but it removes one of the most important barriers. Energy transfer efficiency also mattered. In warm oceans, metabolic processes operate differently. Growth rates can be faster. Reproductive cycles can shorten. Populations can rebound more quickly from losses. This does not mean that ancient oceans were reckless or unstable. It means that they could absorb predation pressure without collapsing. A predator removing a large animal from the system did not necessarily cause cascading failure. Replacement was possible. Another often overlooked factor is oxygen distribution. While it is true that warmer water holds less oxygen than cold water, circulation patterns in ancient oceans mitigated this effect. Frequent mixing, driven by storms and currents, replenished surface oxygen. Productive plankton communities generated oxygen through photosynthesis. Large, active animals could thrive in these conditions without being constrained by respiratory limits. The scale of ancient oceans also played a role. Continents were arranged differently. Ocean basins were shaped in ways that encouraged broad circulation rather than confinement. Gyres moved heat and nutrients across hemispheres. Seasonal changes did not trap water masses in isolation. This openness allowed large predators to roam freely, following prey across thousands of kilometers without encountering abrupt ecological dead ends. Time itself was a resource. Modern ecosystems are often studied over decades at most. Ancient systems evolved over millions of years under relatively stable conditions. This allowed slow but profound adaptations to accumulate. Body size could increase gradually, without being punished by sudden environmental reversals. Energy strategies could refine themselves over countless generations. The result was not a fragile giant, but a well-integrated component of its ecosystem. When scientists talk about Megalodon as an apex predator, it is important to understand what that meant in context. Apex does not mean solitary or rare. In healthy systems, apex predators exist in numbers sufficient to shape prey behavior and population dynamics. That requires an ecosystem capable of supporting not just one giant, but many. Ancient oceans could do this because their energy budgets were vast. There is also the matter of temperature stability. While seasonal variation existed, long-term temperature swings were slower and less extreme than those caused by rapid, modern climate change. This stability allowed large animals to invest in growth without risking sudden mismatch between body size and available resources. Predictability favours size. Chaos favours small, fast-reproducing organisms. Ancient oceans lean toward predictability. It is tempting to imagine Megalodon as an outlier, a monster surviving against the odds. In reality, it was a logical outcome of an environment that made large size advantageous. The ocean fed it not through miracles, but through systems that were scaled-up versions of processes we still observe today. Primary production, energy transfer, redundancy, and time did the work. Eventually, these conditions changed. Continental rearrangement altered circulation. Antarctica became isolated. Ice began to dominate. Nutrients were locked away. Productivity patterns shifted. The same processes that once fed the impossible began to restrict it. Giants lost their advantages. Smaller, more flexible predators gained ground. The ocean did not fail. It adapted. But before that adaptation reshaped everything, there was an era when the sea could afford extravagance, when energy was abundant enough that evolution could experiment boldly, when feeding the impossible was not an exception, but a phase. Understanding that phase requires letting go of modern limits and recognizing that Earth's oceans have worn many faces. Some were lean and selective. Others were generous to the point of excess. The ancient southern oceans belonged firmly to the latter category, and it was within that generosity that creatures like Megalodon found the space, the food, and the time to become what they were. Long before ice caps settled into permanence at the poles, long before Antarctica became a synonym for cold and remoteness, the ocean was already experimenting with scale. This was a world where temperature gradients were gentler, where coastlines stretched wide and shallow, and where the sea did not yet impose the sharp boundaries that would later define survival. In that world, Megalodon did not arrive suddenly or dramatically. It emerged slowly, almost quietly, as a response to conditions that made size not just possible, but advantageous. The absence of permanent ice caps mattered more than it might seem at first glance. Ice is not just frozen water, it is a regulator. It locks away fresh water, alters sea levels, redirects currents, and reflects sunlight back into space. When ice caps are absent or minimal, the planet behaves differently. Sea levels rise, continental shelves expand, warmth spreads more evenly from equator to pole. The ocean becomes less fragmented, more continuous, and far more forgiving to large mobile animals. In this ice-free or ice-light world, sharks were already successful. They had survived multiple extinction events. They had refined their designs for hundreds of millions of years. Cartilage skeletons reduced weight. Replaceable teeth allowed constant renewal. Highly sensitive sensory systems made them efficient hunters, even in murky water. Megalodon did not invent these traits. It inherited them. What changed was the scale at which they could be applied. As marine ecosystems grew richer, prey animals grew larger. This was not coincidence. Abundant food allows prey to invest in body mass, insulation, migration, and reproduction. Early whales began to diversify, moving away from land and fully committing to life in the ocean. Some filtered small organisms, others hunted fish and squid, and many grew quickly to sizes that reduced predation risk from smaller hunters. Size for prey was protection. But protection is relative. As prey animals crossed new thresholds of size and energy content, they opened a new opportunity. A predator capable of exploiting that energy efficiently would gain a tremendous advantage. This is where Megalodon's rise begins to make sense. It was not chasing small, fast fish in crowded reefs. It was targeting large, slow, calorie-rich animals in open water. Growing to such enormous size required more than just good genes. It required a world that could support long growth periods. Megalodon likely took decades to reach full size. During that time, it needed steady access to food, stable temperatures, and expansive territory. An ice-free planet provided all three. Warm waters supported high metabolic rates. Expanded shelves and open migration routes reduced competition bottlenecks. Prey populations rebounded reliably enough to sustain long-lived predators. One of the most important advantages of size in this environment was efficiency. Large animals lose heat more slowly. They can travel farther on the same amount of energy. They can survive longer between meals. In a world without ice caps, where temperature extremes were muted, these advantages compounded rather than conflicted. Megalodon could patrol immense ranges, following prey across oceans that had fewer thermal barriers and fewer ecological dead ends. Its teeth tell part of this story. Megalodon teeth are thick, serrated, and built for cutting through bone. They are not optimized for delicate prey. They are tools designed for dismantling large bodies. Fossil evidence suggests bite forces capable of crushing ribs and disabling massive animals quickly. This level of specialization only makes sense in a world where such prey was consistently available. Nursery grounds also played a role. Like many large sharks, Megalodon likely relied on shallow protected coastal areas for its young. Expanded continental shelves provided these environments in abundance. Warm, shallow waters offered safety from larger predators and ample food for juveniles. This increased survival rates during the most vulnerable stages of life, allowing populations to sustain themselves despite low reproductive rates typical of large sharks. The lack of ice also influenced ocean chemistry. Without large volumes of fresh water locked in glaciers, salinity levels were more stable. Circulation patterns mixed surface and deep waters more freely. Nutrients remained accessible. Oxygen distribution supported active lifestyles. All of this favoured large, continuously swimming predators that depended on efficient respiration and muscle performance. Competition existed, of course. Megalodon was not alone. Other large predators hunted the same seas, including ancestral forms of modern sharks and early-toothed whales. But competition in rich systems does not necessarily eliminate giants. It can refine them. Predators specialize, partition niches, and evolve strategies that reduce direct conflict. Megalodon's sheer size may have been its niche, allowing it to dominate encounters and claim prey that others could not handle. Another subtle but important factor was time. The world without ice caps persisted for millions of years. This stability allowed evolutionary experiments to unfold without being cut short. Megalodon did not need to adapt to rapid, unpredictable shifts. It could fine-tune its growth patterns, hunting strategies, and life history traits in an environment that rewarded consistency. This is how giants are built, not in bursts but through patience. As Megalodon populations spread, they became global. Fossils appear across multiple continents, indicating a wide distribution. This was possible because the ocean was not compartmentalized the way it is today. Warm currents connected distant regions. A predator could move from one productive area to another without crossing hostile zones. The sea was a continuous hunting ground. The rise of Megalodon was therefore not an act of defiance against nature, it was cooperation with it. The planet offered abundance, and evolution responded by pushing size upward. The shark's success reinforced its own trajectory. Large predators influence prey behaviour, which can drive prey to grow larger or migrate differently, which in turn reinforces the advantage of a large hunter. These feedback loops can persist as long as the underlying conditions remain favourable. Eventually those conditions began to erode. Ice caps did form, currents reorganised, Antarctica became isolated. But during the long interval before that transformation, the ocean allowed extravagance. It allowed a predator to grow beyond what seems reasonable by modern standards. It allowed Megalodon to become not a mythic monster, but a logical outcome of a warm, open, generous sea. Understanding its rise requires seeing the planet as it was, not as it is. A world without ice caps was not just warmer, it was wider, deeper in opportunity, and far more permissive of extremes. In that world, the rise of Megalodon was not surprising. It was expected, and as the climate slowly shifted and the sea began to narrow its generosity, the very traits that once made such giants successful would become vulnerabilities, setting the stage for the next transformation in the ocean's long history, where abundance would give way to constraint and size would no longer be the safest answer. Size is often treated as a mystery in nature, something excessive or indulgent, as if growing large were a kind of evolutionary vanity. But in ecosystems where food is reliable, abundant, and widely distributed, size is not a luxury, it is a strategy. It emerges not because nature is reckless, but because the rules quietly favour it. When food never truly runs thin, when energy flows steadily through a system, the balance shifts away from speed and short lives and toward endurance, efficiency, and scale. In environments shaped by scarcity, small bodies dominate. Small animals need less food. They reproduce quickly. They recover faster after losses. These traits are ideal when resources fluctuate unpredictably or collapse entirely. But in environments defined by consistency, the advantages invert. When food is plentiful across seasons and years, being small no longer offers the same protection. Instead, it becomes a limitation. Large bodies store energy. Fat, muscle, and sheer mass act as buffers against short-term shortages. A large predator can miss meals without immediate danger. It can wait, patrol, and choose opportunities rather than reacting to every fluctuation. This matters enormously in the ocean, where prey can be patchy even in productive systems. Abundance does not mean uniform distribution. It means that over time, enough energy exists to support those who can access it efficiently. Efficiency is where size begins to dominate. In water, large animals move differently than small ones. The physics of swimming favour scale. Larger bodies glide more effectively, losing proportionally less energy to drag. Each tail stroke covers more distance. Long-distance travel becomes cheaper, not more expensive. This allows large predators to exploit wide territories, following prey migrations rather than waiting for food to come to them. In ancient oceans, where continental shelves were broad and currents interconnected regions, this ability was decisive. Food did not exist in isolated pockets. It existed across vast, semi-predictable zones. Plankton blooms fed fish. Fish fed larger animals. Marine mammals followed these patterns over enormous distances. A predator capable of matching that scale gained access to an almost continuous food supply. Where food never truly runs thin, growth becomes an investment rather than a gamble. Energy put into body size pays dividends over decades. Larger animals often live longer, reproduce more times, and dominate competitive encounters. In predator-prey dynamics, size can reduce risk as much as it increases reward. A larger predator is less likely to be injured during a hunt. It can subdue prey faster. It can deter competitors without physical conflict. This matters because injury is often more dangerous than starvation. A small predator that is injured may starve even in a rich environment. A large predator, protected by mass and strength, can absorb impacts that would be fatal to smaller hunters. In oceans filled with large prey animals, this advantage compounds. Each successful hunt reinforces the value of size. Another often overlooked factor is thermal stability. Large bodies change temperature more slowly. In warm oceans with seasonal variation, this allows large animals to remain active across a broader range of conditions. They are less vulnerable to short-term cooling or shifts in water masses. This stability supports continuous foraging and movement, further smoothing energy intake over time. Food abundance also reshapes competition. In scarce systems, competition is fierce and immediate. Every calorie matters. In rich systems, competition becomes more strategic. Predators can specialize. Some target small, fast prey. Others focus on large, energy-dense animals. Size allows access to niches that smaller predators cannot exploit. Rather than competing directly, predators partition the ecosystem, reducing conflict and increasing overall stability. In ancient oceans, this partitioning supported diversity at multiple scales. Small fish filled reefs and coastal zones. Medium predators patrolled open shelves. Giants roamed deeper waters and migration corridors. Each level reinforced the others. Removing energy at the top did not collapse the system because energy input at the base remained strong. Plankton continued to grow. Fish continued to spawn. The system absorbed losses without unravelling. Reproduction also behaves differently where food is abundant. Large animals tend to reproduce more slowly, investing heavily in fewer offspring. This strategy fails in unstable environments, but it thrives where survival rates are high. Warm, productive seas with extensive nursery grounds allow young to grow with relatively low mortality. Over time, this supports stable populations of large-bodied animals despite low birth rates. This is particularly important for large predators. Their populations are never dense. They do not need to be. They need consistency. A small number of successful offspring per generation is enough when adults live long lives and face few threats. In ancient oceans, this balance was achievable because food webs were deep and resilient. There is also a psychological aspect to size, not in the animal's mind, but in the system's behaviour. Prey species respond differently to large predators than to small ones. The presence of a giant changes migration patterns, grouping behaviour and habitat use. These responses can actually stabilise prey populations by preventing overgrazing or overcrowding in certain areas. The predator becomes a regulating force rather than a destabilising one. When food never runs thin, ecosystems tolerate regulation. They adjust. They reorganise. They do not collapse at the removal of a few large individuals. This tolerance is what allows giants to persist without exhausting their own resource base. It is a balance achieved slowly, refined over millions of years. Contrast this with modern oceans. Productivity still exists, but it is uneven. Human activity compresses food webs. Overfishing removes mid-level predators and prey. Climate change disrupts circulation. In such systems, size becomes risky again. Large predators struggle not because they are inefficient, but because the system no longer supports their strategy. In the ancient southern oceans, that support was present. Food did not arrive as rare windfalls. It flowed continuously, shaped by sunlight, nutrients, and circulation. Under those conditions, evolution did what it often does when constraints loosen. It explored the upper limits. Size thrives not because it is impressive, but because it solves problems. It solves the problem of distance. It solves the problem of competition. It solves the problem of uncertainty. When food never truly runs thin, those solutions are rewarded again and again. And it is within that quiet logic that giants emerge. Not suddenly, not dramatically, but steadily, generation by generation, as the ocean proves itself capable of feeding something that would otherwise seem unreasonable. An ocean that can sustain giants is never still. Beneath the surface, even on the calmest days, water is always moving, always exchanging heat, matter, and energy. This motion is not background noise. It is the mechanism that turns sunlight into food, minerals into life, and geography into opportunity. In the ancient southern oceans, long before ice reshaped circulation, this motion operated on a scale, and with a freedom that is difficult to replicate today. Currents flowed without the barriers we now take for granted, nutrients cycled efficiently, and the sea remained in a constant state of quiet redistribution. To understand why this mattered so much, it helps to think of the ocean not as a container, but as a conveyor. Nutrients do not simply exist in the water waiting to be consumed. They must be lifted, mixed, and delivered repeatedly. Phytoplankton, the base of the marine food web, require sunlight and nutrients at the same time. Sunlight penetrates only the upper layers of the ocean. Nutrients tend to sink. Motion is what brings them together. In ancient oceans, circulation patterns were shaped by different continental arrangements and different temperature gradients. Without permanent polar ice caps, the contrast between equatorial and polar temperatures was reduced. This softened the global circulation system. Instead of sharp boundaries between warm and cold water masses, there were broad transition zones where mixing occurred continuously. These zones were extraordinarily productive. Currents transported warm water toward the poles and cooler water back toward the equator, but they also carried dissolved nutrients and microscopic life along with them. Plankton populations did not remain isolated. They spread, bloomed, declined, and reappeared elsewhere. This constant redistribution prevented exhaustion. Areas that were temporarily depleted could recover as new nutrients arrived. Areas that experienced blooms fed surrounding regions through drift and decay. Upwelling played a particularly important role. In many regions, winds and currents caused deep, nutrient-rich water to rise toward the surface. This process injected fresh material into sunlit layers, triggering bursts of productivity. In ancient southern oceans, upwelling zones were likely more widespread and persistent due to the lack of strong circumpolar isolation. Nutrients that sank in one region could be returned to the surface elsewhere, rather than being trapped in deep basins. Rivers added another layer to this system. Ancient Antarctica, supporting vegetation and rainfall, delivered fresh water and minerals into coastal seas. These inputs did not simply dilute the ocean, they fertilized it. Sediments carried iron, phosphorus, and organic material that fueled microbial and planktonic growth. Estuaries and nearshore zones became hotspots of activity, feeding larger systems beyond them. The interaction between currents and continental shelves amplified these effects. When water flows across shallow regions, it stirs sediments, releasing trapped nutrients back into circulation. This recycling kept shelves productive over long periods. In modern oceans, many shelves are interrupted by steep drop-offs or limited by ice. In the past, extended shelves around Antarctica allowed motion to interact with the seafloor across vast areas. Endless motion also meant endless opportunity for movement. Large predators rely on predictable pathways. They do not wander randomly. They follow currents, temperature fronts, and prey migrations. In ancient oceans, these pathways were stable over evolutionary timescales. Currents did not abruptly reorganize every few thousand years. They persisted, allowing animals to adapt their life histories around them. For a giant predator, this stability was critical. Megalodon did not need to memorize the ocean, but its ancestors evolved behaviors aligned with persistent patterns. Where currents concentrated prey seasonally, predators followed. Where nutrients fueled blooms, prey gathered. Motion created structure, and structure allowed scale. Another consequence of constant motion was oxygen distribution. Stagnant water becomes depleted. Moving water breathes. Ancient oceans, stirred by winds and unconstrained by ice cover, maintained oxygenated surface layers suitable for active animals. Photosynthesis added oxygen during productive periods, while circulation spread it laterally. Large predators could maintain high activity levels without encountering hypoxic barriers. Motion also shaped temperature distribution. Instead of abrupt cold traps near the poles, warmth extended farther south. Seasonal cooling still occurred, but it was moderated by heat transport. This reduced thermal shock and allowed animals to remain active across wider ranges. For large-bodied animals, avoiding extreme cold was essential. Motion helped ensure that cold did not dominate for long. Perhaps most importantly, endless motion prevented collapse. Ecosystems fail when energy becomes trapped or isolated. In ancient southern oceans, energy moved, nutrients cycled, life adjusted. When one region declined temporarily, others compensated. This resilience is what allowed food webs to grow deep and layered without becoming fragile. From the smallest plankton cell to the largest predator, everything depended on this motion. Remove it, and abundance collapses. Restrict it, and size becomes a liability. Allow it to flow freely, and the ocean becomes capable of sustaining forms that seem excessive by modern standards. As ice eventually returned and circulation patterns tightened, this endless motion slowed. Currents became barriers instead of bridges. Nutrients sank and stayed sunk. Productivity concentrated into fewer regions. Giants that depended on wide, moving systems found their world shrinking. But during the long interval before that change, the ocean remained in motion, quietly generous, endlessly redistributing what life needed to grow. And within that moving framework, the foundation was laid for the next layer of the story, where abundance translated not just into growth, but into entire communities of large prey that would further reinforce the dominance of giants moving through the southern seas. Long before whales became the familiar giants we picture today, gliding slowly through modern oceans and filtering clouds of plankton or singing across vast distances, they were something else entirely. They were experiments, transitional forms, a series of evolutionary attempts to solve the problem of living large in the sea, at a time when the ocean itself was still deciding what kinds of giants it could support. These early whales did not fit neatly into the categories we use now, and understanding them is essential to understanding how predators like Megalodon could thrive in the same world. The earliest ancestors of whales began on land. That much is well established. But what matters for this story is not their terrestrial origin, but the speed and direction of their transformation once they committed to the water. They did not ease slowly into marine life over hundreds of millions of years. They moved decisively. Limbs reshaped, bodies elongated, tails flattened. Hearing adapted to water. Breathing shifted to surface intervals. Within a relatively short geological window, whales became fully aquatic animals. This transition coincided with a time when the oceans were unusually accommodating. Warm temperatures reduced metabolic stress. High productivity ensured abundant food. Shallow seas and broad shelves created safe zones for experimentation. In this environment, whales were free to explore body size, feeding strategies, and ecological roles without being immediately punished for inefficiency. Early whales were not gentle filter feeders drifting through plankton blooms. Many were active hunters. They chased fish. They grabbed squid. Some had teeth suited for tearing flesh rather than straining microscopic prey. Others combined traits, experimenting with mixed strategies that would later disappear as ecosystems reorganized. This diversity mattered because it created a wide range of prey profiles for predators higher up the food web. As whales diversified, they began to occupy niches that had previously been filled by large fish or marine reptiles. They became new sources of dense energy. Muscle, fat and bone packaged into mobile bodies that migrated predictably and reproduced slowly. For a large predator, This was a fundamental shift. Instead of relying on countless small prey, a single successful hunt could provide enormous caloric return. The oceans responded to this new presence. Predation pressure increased, competition intensified, whales adapted by growing larger, swimming faster, or grouping together. Each adaptation pushed the system further towards supporting scale. Large prey encourages large predators. Large predators, in turn, influence the behavior and evolution of prey. This feedback loop does not require conscious intent. It emerges naturally when energy flows allow it. In the southern oceans, this dynamic unfolded across vast spaces. Whales moved along migration routes shaped by currents and productivity. They followed seasonal abundance, travelling between feeding grounds and breeding areas. These movements were not random. They were structured by the same circulation patterns that fueled plankton blooms and fish populations. Predictability emerged at scale. For a predator like Megalodon, predictability was opportunity. Large whales did not dart unpredictably like small fish. They followed routes. They gathered in certain areas at certain times. They surfaced regularly to breathe. These patterns created windows of vulnerability that a powerful, fast-moving predator could exploit. It is important to recognize that early whales were not uniformly massive. Many were medium-sized by modern standards, but still far larger than most fish. Their size alone reduced the number of predators capable of hunting them. This concentrated predation pressure into fewer, larger hunters. Smaller sharks and marine predators were effectively excluded from this energy source. Only animals with sufficient size, speed, and bite force could access it. This concentration further favoured giants. Once a predator reached a certain threshold, it gained access to a resource unavailable to most competitors. This reduced competition and increased efficiency. In rich systems, such thresholds are often crossed. In poor systems, they are not. Another crucial aspect of early whales was their life history. They reproduced slowly. They invested heavily in each offspring. This strategy works only when adult survival rates are high. In ancient oceans with fewer barriers and fewer abrupt environmental shocks, adult whales could live long enough to offset low reproduction rates. This stability allowed whale populations to grow to sizes sufficient to sustain specialized predators. Fat also played a role. Many whales developed thick layers of blubber, not primarily for insulation at first, but for energy storage. Fat is an extraordinarily dense energy source. For a predator, targeting an animal rich in fat is far more efficient than targeting lean prey. This efficiency matters at large scales. It reduces hunting frequency and increases survival during lean periods. As whales grew larger and fattier, they reshaped marine ecosystems. Their feeding behaviours redistributed nutrients. Their waste fertilised surface waters. Their carcasses, when they died, sank to the seafloor, creating localised ecosystems that persisted for decades. Even in death, they contributed energy back into the system. All of this reinforced abundance. The ocean did not simply tolerate whales, it integrated them. And once integrated, they became pillars of the food web. Remove them, and the system would change dramatically. Add predators capable of exploiting them, and the system would adjust again. This is where Megalodon fits not as an intruder, but as a participant. It did not disrupt a fragile balance, it joined a robust one. Its presence likely influenced whale behaviour, encouraging grouping, migration shifts, and perhaps even size increases. These changes, in turn, reinforced the advantage of a predator capable of dealing with large prey. The relationship between early whales and large predators was not static, it evolved continuously. As whales adapted, predators adapted. As predators refined their strategies, whales responded. Over millions of years, this back and forth produced animals far larger than anything seen today. The ocean, during this time, had the capacity to support that escalation. Modern whales are the survivors of this process, shaped by later cooling, ice formation, and the loss of certain predators. Without Megalodon and similar giants exerting pressure, some whale lineages shifted toward filter feeding and extreme size as a different solution. Others disappeared. What we see today is not the peak of whale evolution, but one outcome among many. Looking back at whales before whales as we know them requires letting go of familiar images. These were not gentle icons of conservation. They were active participants in competitive, dynamic ecosystems. They were prey as well as predators. They were energy stores moving through open oceans that had not yet been narrowed by ice and isolation. In that world, their existence made giants viable. They provided the calories, the predictability, and the evolutionary pressure that allowed predators like Megalodon to rise and persist. Without them, size at the top of the food web would have been far more difficult to sustain. As the climate cooled and the southern oceans began to change, these relationships would be tested. Some would break, others would transform. But before that transformation, there was a long stretch of time when whales were not yet what we recognise today, and the ocean was rich enough to let both hunter and hunted grow beyond what seems reasonable now. That richness did not come from chance. It came from structure, from motion, and from systems that rewarded scale. And it is from within that system that the next question naturally follows, because once whales existed as abundant, energy-rich prey, the dynamics of predation itself began to shift, pushing the balance between hunter and hunted into a new and even more extreme phase. Apex predators do not arise in desperate places. They do not flourish where every meal is a gamble or where survival depends on constant improvisation. True apex predators emerge where systems are stable enough to absorb pressure, where energy moves reliably from the bottom of the food web to the top, and where the removal of large prey does not unravel everything beneath it. In other words, apex predators are not signs of fragility. They are signs of comfort, of abundance so deep that it can afford regulation. In the ancient southern oceans, abundance was not subtle, it was structural. It was built into the way energy entered the system, how it moved, and how it was recycled. This kind of abundance creates a very specific ecological outcome. It allows predators at the top to exist not as rare anomalies, but as consistent forces shaping the behaviour of everything below them. An apex predator is not defined simply by size or ferocity. It is defined by position. It occupies a role where it has few or no natural enemies, where its main limitations are energy intake, reproduction, and long-term environmental change rather than daily survival. To reach that position, an ecosystem must first solve several problems. It must produce enough prey, it must do so consistently, and it must do so across enough space that a large predator can move, hunt, and reproduce without exhausting local resources. In ecosystems driven by scarcity, apex predators are unstable. They appear briefly and disappear quickly. Any disruption cascades upward, and the largest animals are the first to go. But in ecosystems shaped by abundance, the opposite happens. The system buffers shocks. Prey populations recover, predators persist. The apex position becomes durable rather than precarious. This durability is what allowed predators like Megalodon to exist not just as isolated giants, but as established components of the marine world. Its presence implies that prey populations were not only large, but resilient. It implies that energy removal at the highest level did not collapse lower levels. That kind of resilience only appears when productivity at the base is immense, and when energy transfer pathways are efficient. Comfort in this sense does not mean ease, it means predictability. For a large predator, predictability is more valuable than sheer quantity. Knowing that prey will appear in certain regions at certain times allows a predator to plan, to migrate, to grow large without constant risk. Ancient oceans provided this through stable currents, seasonal cycles, and long-term climate consistency. Apex predators also influence abundance in return. They regulate prey behavior, not just numbers. The presence of a large predator alters how prey move, where they gather, and how they feed. This can prevent overexploitation of resources by prey species, indirectly stabilizing the system. In this way, apex predators become part of the machinery that maintains abundance rather than simply consuming it. This feedback loop is often misunderstood. Apex predators are sometimes portrayed as threats to ecosystem health. In reality, in systems that can support them, they are often signs that the system is functioning well. Their disappearance, rather than their presence, is frequently the warning sign. In ancient southern oceans, apex predators existed alongside one another. Megalodon was not alone at the top. Other large sharks and early-toothed whales competed for similar resources. This competition did not eliminate giants, it refined them. Each predator adapted strategies to reduce direct conflict. Some focused on different prey sizes, others specialized in different regions or hunting styles. The result was a layered apex rather than a single dominant hunter. Layered apex systems are only possible where food webs are deep. Shallow food webs collapse under pressure, deep ones redistribute it. When multiple apex predators coexist, it means the system is producing more energy than any single predator can monopolize. That surplus allows diversity at the top. Comfortable abundance also changes risk tolerance. Large predators can afford patience. They do not need to attack every opportunity. They can wait for optimal conditions. This reduces injury risk and increases lifespan. Over time, this favors body plans that emphasize strength and efficiency over frantic speed. Megalodon's build reflects this. It was not built for endless chases. It was built for decisive encounters. Another consequence of abundance is learning. Long-lived predators can accumulate experience. They can refine hunting strategies over decades. They can pass behaviors through generations, whether genetically or through social mechanisms. While sharks do not exhibit culture in the human sense, long-lived individuals still benefit from experience in navigating complex environments. This experience reinforces the apex role. A predator that survives long enough to master its environment becomes increasingly efficient, further stabilizing its position. In contrast, in harsh environments where lifespans are short, such refinement never occurs. Abundance also shapes reproduction. Apex predators typically reproduce slowly. They invest heavily in each offspring. This strategy only works when juvenile survival rates are reasonably high. In ancient oceans with extensive nursery grounds and fewer abrupt disruptions, young predators had a better chance of reaching maturity. This allowed populations to sustain themselves without rapid reproduction. The comfort of abundance extended beyond food. It included space. Ancient oceans offered room to roam. Migration routes were long and unobstructed. There were fewer ecological bottlenecks where predators and prey were forced into intense competition. This spatial freedom reduced stress on populations and allowed large predators to distribute their impact rather than concentrating it. As the climate cooled and ice began to return, this comfort eroded. Abundance became patchier. Predictability declined. Apex positions grew more fragile. Large predators faced increasing constraints. Some adapted, others disappeared. The disappearance of giants like Megalodon was not caused by a single failure, but by the gradual loss of the conditions that made apex dominance comfortable rather than risky. Understanding apex predators in this context changes how we view them. They are not reckless consumers pushing systems toward collapse. They are responses to systems that can support regulation at the highest level. Their existence tells us something about the world they lived in. It tells us that the ancient southern oceans were not marginal or extreme, but rich, stable, and forgiving enough to allow life to explore its upper limits. As the story continues, this perspective becomes increasingly important, because once apex predators are established within a comfortable, abundant system, their fate becomes tightly linked to changes in that system. And as the southern oceans slowly lost their openness and generosity, The very forces that once supported giants would begin to turn against them, reshaping the balance between abundance and survival in ways that no predator, no matter how large, could ignore. Life in the far south has always been shaped by light, or more precisely by its uneven distribution. Even in warm eras, even when ice had not yet claimed the continent, the southern regions experienced something that never changed: extreme seasonality. The sun did not rise and set in gentle, predictable rhythms as it does near the equator. Instead, it lingered. It disappeared. Months of brightness were followed by months of darkness. This pattern did not prevent life from thriving. It forced it to adapt in ways that favoured flexibility, endurance, and timing. In a world without ice caps, dark winters did not mean frozen seas. Water temperatures remained relatively mild, buffered by global warmth and ocean circulation. But darkness still mattered. Photosynthesis slowed or stopped. Primary production dipped. The base of the food web tightened. Then, when the sun returned, it did so with intensity. Long summers flooded the ocean with light, triggering explosive growth. Plankton bloomed rapidly. Energy surged upward through the system. The contrast between scarcity and abundance became a defining rhythm. This rhythm shaped everything. Species that survived here did not rely on constant conditions. They relied on cycles. They evolved to anticipate change rather than resist it. Some stored energy, some migrated, some slowed their metabolism, others synchronized reproduction with the return of light. Adaptation was not about avoiding darkness, but about using it. For large marine predators, this seasonal structure offered both challenges and opportunities. During long summers, prey populations expanded dramatically. Fish spawned. Marine mammals fed heavily. Juveniles grew quickly. For predators capable of exploiting this surge, the rewards were enormous. A successful season could sustain an individual for long periods. Fat reserves built up. Growth accelerated. Reproductive energy accumulated. During darker months, activity patterns shifted. Prey dispersed or migrated. Some descended into deeper waters. Others moved toward lower latitudes. Large predators did not need to feed constantly. Their size allowed them to bridge these gaps. They could follow prey migrations or remain in productive regions where residual activity persisted. Darkness did not halt life. It redistributed it. This redistribution favoured mobility. Animals that could move efficiently over long distances had an advantage. They were not trapped in local downturns. They could follow the shifting edge of productivity. In ancient southern oceans, where currents connected regions broadly, this movement was feasible. Seasonal change did not create dead ends. It created gradients. Adaptation to light cycles also shaped sensory systems. In dim or variable lighting, vision alone is unreliable. Many marine predators rely heavily on other senses. Sharks, in particular, evolved extraordinary abilities to detect electrical signals, pressure changes, and chemical cues. These senses do not depend on light. In long polar nights, they remain fully functional. Darkness becomes less of a limitation and more of a filter, excluding species that rely too heavily on sight. Prey species adapted as well. Grouping behaviour increased during vulnerable periods. Migration timing became more precise. Calving and breeding synchronized with predictable windows of abundance. These adaptations made prey populations more resilient, but they also made them more predictable. Predictability, for a large predator, is a form of access. The alternation between dark winters and long summers also shaped growth strategies. In highly seasonal environments, growth often occurs in pulses. Rapid expansion during favourable periods is followed by maintenance during leaner ones. Over evolutionary time, this can favour organisms that grow large quickly, when conditions allow, and then stabilise. For a predator like Megalodon, this meant that juvenile growth could be accelerated during productive seasons, reducing vulnerability and increasing survival. Long summers had another important effect. Extended daylight allowed photosynthesis to operate nearly continuously for months. This led to sustained plankton blooms rather than short bursts. Energy input was not just high, but prolonged. The system did not need to reset every day. It could build momentum. This momentum carried through the food web, supporting larger biomass at higher levels. Dark winters, meanwhile, reduced competition. Some species could not tolerate prolonged darkness or lower productivity. They retreated or declined seasonally. Those that remained faced fewer rivals. Large predators capable of enduring these periods benefited from reduced competition when prey was still available. Endurance became as valuable as aggression. Adaptation to seasonality also influenced reproduction timing. Giving birth or hatching young during peak abundance increased survival. In ancient southern seas, nursery grounds aligned with summer productivity. Shallow, warm waters filled with food provided ideal conditions for juveniles. This alignment reinforced population stability even for species with slow reproductive rates. Importantly, these adaptations did not evolve in isolation. They co-evolved. Prey adapted to predators. Predators adapted to prey. Both adapted to the light cycle. Over millions of years, this produced ecosystems finely tuned to extreme seasonality without being fragile. Change was expected. It was built into the system. This context matters because it explains why large predators were not disadvantaged by polar conditions even before ice arrived. Darkness did not equal emptiness. It equalized the playing field for species that could sense, move, and endure. Warm water ensured that metabolic processes continued. Circulation ensured that nutrients did not stagnate. Light returned reliably. The system breathed in a slow, powerful rhythm. As ice eventually advanced and darkness became paired with cold, this balance shifted. Endurance alone was no longer enough. Mobility faced thermal barriers. Productivity patterns compressed. Adaptations that once thrived became liabilities. But before that turning point, dark winters and long summers did not suppress giants. They shaped them. They selected for animals that could wait, move, and exploit opportunity when it appeared. They rewarded size, efficiency, and patience. And within that seasonal pulse, the ancient southern oceans remained capable of sustaining predators that seem almost implausible today, not despite their cycles of light and dark, but because of them. Cold has a reputation it does not entirely deserve. In human experience, cold is often paired with absence. Fewer people outside, fewer plants growing, fewer signs of activity. It is easy to assume that low temperatures naturally strip environments of life, reducing them to sparse marginal systems barely holding on. But in the ocean, temperature alone is a poor predictor of abundance. What matters far more is movement, nutrients, and structure. When those are present, cold does not mean empty. In some cases, it means the opposite. Even today, some of the most biologically productive marine regions on Earth are cold. The waters of the Southern Ocean support enormous populations of krill, which in turn sustain whales, seals, penguins, and seabirds. The North Atlantic, despite its chill, has long supported dense fisheries. These systems thrive not because they are warm, but because they are dynamic. They are mixed. They are fed continuously by nutrients brought up from depth. Cold in these cases preserves rather than suppresses energy. In ancient oceans, this principle was even more pronounced. Cold periods did not arrive suddenly or uniformly. Cooling happened gradually, unevenly, and often without immediate ice formation. Water temperatures could drop while circulation remained strong. Nutrients could remain accessible. Productivity could continue, albeit redistributed. Life adapted not by disappearing but by reorganizing. Cold water has physical properties that can favor life. It holds more dissolved oxygen than warm water. This increased oxygen availability supports active metabolisms, particularly in large animals that require efficient respiration. For predators capable of generating and sustaining power, oxygen-rich water is an advantage, not a limitation. Cold also slows decay. Organic matter persists longer, allowing more complete recycling of nutrients. In warmer waters, biological processes move quickly, sometimes too quickly, shunting nutrients out of productive layers before they can be reused. In cooler systems, recycling can be more efficient, sustaining food webs even when primary production slows seasonally. Another overlooked factor is density. Cold water is denser, which enhances vertical mixing under the right conditions. Wind-driven circulation and temperature gradients can stir nutrients upward, fueling plankton growth even when surface temperatures are low. This mixing is one reason polar and subpolar seas can support massive seasonal blooms. In ancient southern oceans, cooling did not immediately create lifeless zones. Instead, it shifted where and when productivity occurred. Some regions became less favourable year-round but highly productive during specific seasons. Others maintained steady output through constant mixing. For animals capable of moving with these patterns, cold did not remove opportunity, it concentrated it. Large predators benefit from concentration. When prey gathers into fewer regions or tighter windows of abundance, a predator capable of travelling long distances and surviving lean periods gains an advantage. Size allows this. Endurance allows this. Cold environments, paradoxically, can reward both. There is also a misconception that cold automatically increases energetic cost. While maintaining body temperature can be expensive for terrestrial animals, marine animals experience a different balance. Water temperature affects metabolic rates, but buoyancy and insulation strategies can offset costs. Fat layers, for example, are not just for warmth, they are energy storage. In cold or cooling environments, fat becomes a dual-purpose adaptation, supporting both thermoregulation and survival during food gaps. In ancient oceans transitioning toward cooler states, animals that already possessed these traits were pre-adapted. Large marine mammals and large predators did not need to reinvent themselves to cope with cooling. They already stored energy efficiently. They already travelled widely. They already tolerated variability. Cold alone did not eliminate them. What cold does change is predictability. As temperatures drop and ice begins to appear, circulation patterns can reorganise. Barriers form. Productivity can become more patchy. This is where the difference between cold and empty becomes important. Cold systems can be full of life if they remain connected and mixed. They become empty when that connectivity breaks down. In the ancient South, before full isolation set in, cold periods still existed within a connected ocean. Currents continued to move, nutrients continued to cycle, life adjusted. Only when Antarctica became ringed by persistent ice and encircled by isolating currents did cold begin to mean exclusion rather than redistribution. This distinction helps explain why giants could persist even as temperatures fell. Megalodon and other large predators were not immediately displaced by cooling. They followed prey into regions that remained productive. They exploited seasonal abundance. They endured periods of scarcity using stored energy. Cold alone was not their enemy. Modern comparisons reinforce this idea. Many large marine animals today thrive in cold waters. Blue whales feed in polar seas. Orcas hunt in icy regions. Elephant seals dive in frigid depths. These animals do not survive despite the cold. They survive because the systems they inhabit remain productive. The ancient oceans that supported giants operated under similar principles. Cold was one variable among many. It shaped distribution, but did not dictate collapse. Life persisted where motion, nutrients, and structure remained intact. Understanding this helps dissolve a false assumption that often clouds discussions of ancient polar life. The assumption that once temperatures dropped, ecosystems must have vanished. In reality, they transformed. Some pathways closed, others intensified. For a time, Cold even enhanced certain advantages for large, adaptable predators. It was not cold itself that eventually narrowed the world for giants. It was isolation. It was the loss of circulation. It was the locking away of nutrients behind ice and depth. Cold became a problem only when it came paired with barriers. Before that pairing was complete, cold seas could still be busy seas. They could still feed immense bodies. They could still support complex food webs. And they could still for a while longer sustain predators that relied on the ocean's ability to remain generous, even as temperatures declined. That realization sets the stage for what comes next. Because once cold begins to reshape not just temperature but movement, the balance shifts. The ocean does not empty overnight, it tightens. And in that tightening, the rules that once favoured size begin to change. The ocean does not change its mind quickly. When it reshapes itself, it does so patiently, layer by layer, current by current, over spans of time that are almost impossible to feel from a human perspective. There was no single moment when the world that supported giants suddenly disappeared. No sharp line where abundance stopped and limitation began. Instead, the environment that had once been wide open slowly began to narrow, not through catastrophe, but through gradual rearrangement. This was the slow closing of a playground that had once seemed endless. At first, the changes were subtle. Continents continued their quiet drift, guided by forces deep within the Earth. Antarctica moved farther south, inching toward a position where sunlight would strike at lower angles and for shorter durations. This alone did not doom the southern oceans. Warmth still arrived via currents. Productivity still pulsed with the seasons. But the geometry of the planet was changing, and geometry matters in the ocean. Ocean gateways began to shift. Passages that once allowed free flow between basins narrowed or closed entirely. Water that had once circulated broadly now found itself constrained, redirected, or slowed. These changes altered how heat moved around the globe. They also altered how nutrients were distributed. Some regions received less replenishment, others became overly mixed. The balance that had sustained widespread abundance began to tilt. One of the most consequential developments was the gradual isolation of Antarctica. As surrounding land masses moved away, deep ocean channels opened that allowed water to flow around the continent uninterrupted. Over time, this flow intensified into what would eventually become a powerful circumpolar current. At first, it was not the barrier it would later become, but even in its early stages, it began to separate southern waters from warmer influences farther north. This separation did not immediately freeze the ocean. Instead, it changed its character. Heat exchange weakened. Seasonal extremes sharpened. Nutrient pathways shifted. The system that had once functioned as a broad, interconnected network began to segment into regions with distinct behaviours. For large predators that depended on continuous access to prey across wide ranges, this segmentation introduced friction. Prey responded first. Migration routes adjusted as currents changed. Some species found new feeding grounds, others lost access to old ones. Population centres shifted. Where food had once been distributed across large areas, it began to concentrate into fewer zones. This concentration did not necessarily reduce total productivity, but it changed how that productivity could be accessed. For a giant predator, concentration is a double-edged sword. On one hand, dense prey gatherings can support efficient feeding. On the other, they increase competition and vulnerability to disruption. When abundance is spread out, predators can move freely, reducing pressure on any one region. When it's concentrated, pressure intensifies. As the southern oceans tightened, large predators were forced into narrower corridors. Their movements became more predictable. Their dependence on specific regions increased. The flexibility that had once allowed them to thrive across hemispheres began to erode. Cooling accelerated these trends. As Antarctica approached its polar position, ice began to persist through summers. At first, it was seasonal. Then it lingered longer each year. Ice altered the ocean in multiple ways at once. It reflected sunlight, reducing surface heating. It freshened surface waters as it melted, changing density and circulation. It physically blocked access to coastal shelves that had once served as nurseries and feeding grounds. The loss of shelves was particularly significant. Shallow coastal zones are among the most productive marine environments. They recycle nutrients efficiently. They support juvenile stages of many species. As ice encroached, these zones shrank or vanished. Food webs that had relied on them were forced offshore or into deeper water, where productivity patterns differed. This transition favoured some animals and disadvantaged others. Smaller, more flexible predators adapted more easily. They required less space. They reproduced faster. They could exploit new niches that opened as others closed. Giants, by contrast, faced a shrinking margin for error. Their size, once an advantage, now required more precise alignment between energy intake and expenditure. The closing of the giants' playground was not uniform. Some regions remained productive longer than others. Warm currents still penetrated certain areas. Seasonal abundance persisted in pockets. For a time, large predators could track these refuges, moving from one to another as conditions allowed. This likely prolonged their persistence well beyond what a simple temperature decline would predict. But refuges are not playgrounds. They are holding patterns. They allow survival, not expansion. Over time, as isolation deepened and ice advanced, the number of viable refuges diminished. Migration routes fragmented. Prey populations became more volatile. Competition intensified. Another subtle shift occurred in the nature of competition itself. As large predators became more constrained, interactions with other apex hunters increased. Early toothed whales, some of which were formidable predators in their own right, began to fill roles once dominated by sharks. Unlike sharks, these mammals could regulate their body temperature internally, granting them access to colder waters and greater endurance in cooling climates. This did not immediately displace giants like Megalodon, but it changed the balance. Where once size alone conferred dominance, now flexibility and thermal independence mattered more. The rules of the system were changing, and they were changing slowly enough that no single adaptation could solve the problem all at once. The ocean also became noisier in a different way. Variability increased. Climatic oscillations introduced unpredictability. Productivity pulses became less reliable year to year. For large predators with slow reproduction, unpredictability is dangerous. A few poor years can have long-lasting effects on population stability. What makes this phase of the story so important is its subtlety. There was no dramatic collapse signalling the end of giants. Instead, there was a long narrowing, a gradual tightening of constraints that accumulated until the strategy of being enormous no longer paid off. The playground did not vanish. It became smaller, colder, more segmented. It demanded precision rather than scale. It rewarded adaptability over dominance. Giants could survive in it for a while, but they could no longer thrive in the way they once had. This process unfolded over millions of years. It gave predators time to respond, to adjust, to attempt new strategies. Some succeeded by shrinking, specializing, or shifting diets. Others faded as the margins closed. Megalodon, built for a world of openness and abundance, found itself increasingly out of alignment with the ocean it had once mastered. Understanding this slow closing helps explain why the disappearance of giants was not abrupt. It was not the result of a single failure or sudden disaster. It was the outcome of an environment that gradually withdrew the conditions that had made such size viable in the first place. As the southern oceans continued to cool and isolate, the playground became a corridor, then a series of rooms, and finally a maze. Navigating it required traits that giants were not designed to prioritize, and in that shifting maze, the story begins to turn toward the final stages of coexistence between ancient abundance and emerging constraint, where the question is no longer how giants rose, but how long they could continue to hold on. Ice did not arrive all at once. It crept in. It tested the edges of the system before claiming its centre. Long before Antarctica became the frozen continent we recognise today, ice began to return in quieter ways, appearing seasonally, lingering a little longer each year, reshaping the ocean not through sudden violence, but through persistence. And with that persistence, the character of the sea began to change. At first, ice was just another variable layered onto an already dynamic environment. Winters grew colder, snow accumulated on land and lingered into spring, sea ice formed along coastlines and retreated again with the sun. Life adapted, as it always had. Plankton blooms still followed the light, fish still spawned, large predators still hunted, but the system was no longer operating with the same freedom it once had. Ice alters the ocean in ways that go far beyond temperature. When seawater freezes, it excludes salt, creating dense, salty water beneath the ice that sinks and drives circulation. This process can invigorate deep ocean currents, but it can also disrupt existing patterns. Surface waters freshen, stratification increases. In some regions, nutrients become trapped below layers that sunlight cannot reach. Productivity shifts, not uniformly downward, but unevenly. These uneven shifts are critical. Ancient oceans that once distributed abundance broadly now began to funnel it. Some regions remained highly productive, especially where currents forced mixing, or where seasonal ice melt injected nutrients into surface waters. Other regions became quieter, less reliable, less capable of supporting large populations year after year. The ocean did not empty. It reorganized. As ice expanded, continental shelves changed character. Seasonal ice scoured shallow seafloors, disturbing habitats that had once served as nurseries. In some places, this disturbance increased productivity by releasing nutrients. In others, it made conditions unstable, favouring species that could reproduce quickly and tolerate disruption. The long, predictable growth cycles that had supported slow-growing giants became harder to maintain. Sea ice also reduced light penetration. Even thin ice reflects and scatters sunlight, limiting photosynthesis below. This shortened the effective growing season for plankton, compressing productivity into narrower windows. When blooms occurred, they were intense. When they ended abruptly. This pulsed environment rewarded opportunists and punished those dependent on steady intake. For large predators, this shift mattered. They could still exploit intense blooms and dense prey aggregations, but the gaps between opportunities widened. Reliance on stored energy increased. Migration timing became more critical. Missing a productive window carried greater consequences than it once had. Ice also introduced physical barriers. Seasonal ice fields altered migration routes, forcing animals to detour or concentrate along edges. These edges, where ice met open water, became hotspots of activity. Prey gathered, predators followed. But edges are temporary. They shift with winds and temperatures. What was accessible one year might vanish the next. This instability increased risk. Large predators could no longer rely on inherited patterns alone. Flexibility became more important than size. Animals capable of adjusting diets, shifting ranges quickly, or exploiting a wider variety of prey gained an advantage. The return of ice also amplified competition. As productive areas contracted, more predators were forced into closer proximity. Encounters increased. For animals built to dominate vast open spaces, this crowding reduced the benefits of size. Strength still mattered, but maneuverability, social behaviour and thermal regulation began to matter more. Marine mammals, particularly toothed whales, began to gain ground under these conditions. Their ability to regulate internal temperature allowed them to remain active in colder waters longer than large ectothermic sharks. Their social structures enabled cooperative hunting. Their flexibility in prey choice allowed them to exploit changing conditions more effectively. This was not an immediate replacement, it was an overlap. For a long time, sharks like Megalodon and large marine mammals coexisted in these changing seas, but the balance was shifting. Each incremental advance of ice tilted the system slightly away from strategies that depended on uninterrupted abundance. Ice also affected reproduction indirectly. Nursery grounds that once lay in warm, shallow waters became less reliable as temperatures fluctuated and ice intruded. Juvenile survival rates declined in some regions. For species with slow reproduction, even small declines in juvenile survival can have large long-term effects. The seas themselves became louder in a different way. Increased storminess accompanied changing climate gradients. Wind patterns shifted. Mixing intensified in some areas and weakened in others. This variability made year-to-year conditions harder to predict. Predictability had been a quiet ally of giants. Its loss was significant. Yet it is important not to oversimplify this phase. The return of ice did not immediately exclude large predators from southern waters. In many ways, it enhanced certain forms of productivity. Ice edge ecosystems are famously rich. Nutrient pulses associated with melting ice can support massive blooms. For a time, these blooms could sustain large prey and, by extension, large predators. But ice edge productivity is seasonal and spatially constrained. It requires precise timing. It demands mobility and flexibility. Giants could exploit it, but they could not dominate it in the way they had dominated broader systems. The ocean was no longer a wide plain. It was becoming a mosaic. As ice returned, the seas began to favour different traits. Endurance remained valuable, but adaptability rose in importance. Size alone was no longer enough to guarantee success. The system was asking different questions now, and it would reward different answers. This transition did not signal an immediate end. It signalled a narrowing of options. Giants still existed. They still hunted. They still shaped ecosystems. But they were doing so in an environment that was slowly withdrawing the conditions that had once made their dominance effortless. The return of ice marked the beginning of a new phase in the ocean's long history. A phase where abundance persisted but only in fragments. Where productivity remained high, but only in certain places and times. Where survival depended not just on power, but on alignment with a system that was becoming more selective. As the seas continued to change, the consequences of this selectivity would deepen. The question would no longer be whether giants could survive in cold or ice. It would be whether a world increasingly defined by barriers, pulses, and unpredictability still had room for a predator built for openness, continuity, and scale. For a time, it may have seemed as though Megalodon could simply follow the cold wherever it went. After all, the ocean did not cool uniformly. Warmth lingered in pockets. Productive zones persisted along shifting currents and ice edges. Large prey did not vanish overnight. From a distance, it might appear that a predator capable of crossing entire oceans could simply adjust its range and continue much as before. But following the cold was never the real challenge. Following what the cold eventually did to the ocean was, Megalodon was built for a world defined by continuity. Its success depended on broad, connected systems where energy flowed predictably, and where movement between productive regions was relatively unimpeded. As the climate cooled, those systems did not just move, they fractured. And fragmentation is something size does not handle well. The first limitation was physiological. Megalodon, like modern sharks, was not fully endothermic. It could retain heat better than many fish, especially at large sizes, but it still relied heavily on ambient water temperature to regulate its metabolism. In cooler waters, muscle performance slows. Digestion takes longer. Recovery after exertion becomes more costly. These effects are manageable within certain bounds, but as cold expanded and became more persistent, the energetic margin narrowed. Large size amplifies this problem. A massive body requires continuous oxygen delivery and efficient muscle function. Even small reductions in performance scale upward. What once felt like endurance begins to feel like drag. Following prey into colder regions meant paying higher energetic costs for the same return. Over time, that balance tilts. The second limitation was structural. As ice advanced, it did not simply lower temperatures, it introduced barriers. Sea ice altered coastlines. Glacial fronts blocked access to shallow waters. Ice shelves eliminated nursery grounds and nearshore feeding zones that had once been central to life cycles. For a predator that relied on wide-ranging movement and access to multiple habitat types, these losses were profound. Megalodon could hunt in open water, but its life history likely depended on more than that. Juveniles almost certainly required warmer, protected environments to grow safely. As those environments disappeared or became unreliable, recruitment suffered. Adult predators can endure hardship for years. Populations cannot endure reduced recruitment indefinitely. The third limitation was prey behavior. As cold intensified, prey species adapted in different ways. Some migrated toward lower latitudes. Others evolved insulation, social hunting strategies, or deeper diving habits. Marine mammals, in particular, benefited from internal temperature regulation. They could exploit colder waters more effectively and for longer periods. This shift mattered because it altered vulnerability. Whales and other large prey became harder to catch. They could remain active in colder waters where sharks became less efficient. They could cooperate. They could dive deeper for longer. The prey base that had once rewarded size began to reward flexibility. Competition also changed in character. In warmer, open systems, competition was diffuse. Predators spread out. Encounters were infrequent. As productive zones contracted, predators were forced into closer proximity. Interactions increased. Under these conditions, sheer size is not always the best solution. Agility, cooperation, and thermal independence can outweigh mass. Toothed whales increasingly filled apex roles in colder seas. They hunted in groups. They adapted diets quickly. They exploited acoustic senses rather than relying on ambush alone. Their evolutionary toolkit was better suited to a fragmented, cooling ocean. Megalodon could still compete, but the contest was no longer tilted in its favour. Another challenge was timing. In a world of ice-edge productivity and seasonal pulses, missing a window of abundance could have lasting consequences. Large predators with slow reproduction are especially vulnerable to poor timing. A few unsuccessful seasons can ripple through population structure for decades. As variability increased, risk accumulated. Following the cold also meant following unpredictability. Warm refuges shifted. Currents changed. Ice coverage varied year to year. The inherited patterns that had guided Megalodon's movements became less reliable. Adaptation requires time, and while Megalodon had evolved over millions of years, the pace of environmental change was accelerating relative to its life history. It is important to note that Megalodon did not fail suddenly. It persisted alongside cooling for a long time. Its disappearance was not a dramatic collapse, but a gradual attrition. Populations became more isolated. Genetic exchange weakened. Local extinctions were no longer recolonized easily. What had once been a connected global population became fragmented. Fragmentation is often the final pressure on large species. Once populations are separated, resilience drops sharply. A disturbance that would once have been absorbed by a large network now hits a small group directly. Recovery slows. Variability becomes dangerous. Megalodon's size, once its greatest strength, now worked against it. Large animals adapt slowly. They require stable conditions over long periods to maintain population balance. The cooling ocean was no longer stable in the way it once had been. It was not just colder, it was narrower, more selective, and less forgiving of mismatch. Following the cold forever would have required a fundamental redesign. It would have required faster reproduction, greater thermal independence, more flexible diets, and tolerance for fragmented habitats. These are not traits that evolve quickly in giants. They are traits that favour smaller, more adaptable forms. So Megalodon did not simply fail to chase the cold, it outlived the world that had made chasing worthwhile. The ocean did not remove it violently. It withdrew the conditions that had once supported its strategy, leaving behind a system where size alone could no longer guarantee success. What remained were echoes. Descendants adapted to new rules. Other predators stepped into reshaped roles. The ocean continued, as it always does, adjusting without sentiment. And in the wake of that adjustment, the absence of a giant tells a quieter story than its presence ever did. It tells the story of a world that changed its priorities, slowly but decisively, and of a predator that had once mastered abundance, finding itself increasingly out of step with a sea that no longer needed what it had been built to offer. Even though the giants themselves are gone, the oceans they once ruled still remember them. Not in any conscious way, of course, but in structure, in behaviour, in patterns that make more sense when viewed as remnants rather than inventions. The modern southern oceans are not blank slates rewritten by ice. They are palimpsests, layered with history, where traces of ancient abundance still shape how life moves and organises itself today. Look closely at the Southern Ocean now, and despite its cold, despite its hostility to human comfort, it is anything but empty. It supports immense biomass, much of it concentrated into fewer species than in warmer seas, but at staggering densities. Krill form swarms so vast they can be seen from space. Baleen whales migrate thousands of kilometres to feed there, timing their arrival with precision that borders on ritual. Seals and seabirds follow similar rhythms, gathering where productivity peaks and dispersing when it fades. This concentration is not an accident. It is a direct consequence of the same processes that once supported giants like Megalodon, now operating under tighter constraints. The echoes begin with scale. Modern southern ecosystems are compressed versions of their ancient counterparts. Where productivity was once spread broadly across shelves and open waters, it is now funneled into narrow bands, particularly along ice edges and upwelling zones. These regions act like pressure points in the system, places where energy accumulates rapidly and predictably. They are rich because they have to be. The rest of the ocean offers little margin. This compression favours large animals again, though not in the same way as before. Modern whales grow enormous not because predators demand it, but because filtering vast quantities of small prey is efficient in these concentrated systems. Size allows them to store energy, travel long distances, and exploit short windows of abundance. In that sense, today's whales are living echoes of a time when size was the dominant solution to oceanic living. Behaviour carries echoes as well. Migration routes in the southern hemisphere are ancient. They follow paths carved not by coastlines alone, but by currents that have existed in some form for tens of millions of years. Even as continents moved and ice advanced, the deep structure of circulation persisted. Animals that follow these routes today are responding to the same invisible architecture that once guided predators and prey through warmer seas. Predation itself still bears traces of the past. Modern apex predators in southern waters, such as orcas, exhibit behaviours that make more sense when viewed as inherited responses to ancient pressures. Cooperative hunting, prey specialisation, and strategic targeting of large animals are not new inventions. They are refinements of tactics that evolved in ecosystems where large prey and large predators shaped one another continuously. Even fear leaves echoes. Prey species respond to predators not just through direct encounters, but through inherited tendencies. Grouping behaviour, migration timing, and habitat choice are influenced by evolutionary memory. While Megalodon is long gone, the selective pressures it exerted helped shape the lineage of animals that survived it. Their descendants still carry those adaptations even if the original threat has vanished. The seafloor tells a quieter story. Whale falls, where large carcasses sink and create temporary ecosystems, are reminders of how energy once moved through the system. These events mirror, in miniature, the recycling pathways that were far more common when large animals were more abundant. The communities that form around them are specialised, efficient, and ancient in origin. There are echoes in absence too. Modern southern oceans lack large ectothermic apex predators. Sharks exist, but none approach the scale or dominance of Megalodon. This absence is not because the ocean cannot physically support such animals anymore, but because the system no longer offers the same combination of continuity, predictability and recruitment that once made such size viable. The space where giants once operated has been repurposed, yet the ocean still flirts with the edge of that possibility. During particularly productive years, when ice retreat aligns perfectly with nutrient upwelling and sunlight, the system briefly resembles its ancient self. Biomass surges, prey densities rise, predators gather. For a moment the ocean feels generous again, almost excessive. Then conditions shift and the window closes. These pulses hint at what once was constant. They show that the underlying machinery is still there, constrained but functional. Remove the ice, reconnect the currents, expand the shelves, and the system would likely respond in familiar ways. Not instantly, not identically, but recognisably. The echoes also serve as a warning. Modern changes to the ocean are happening far faster than the ancient transitions that reshaped it before. Giants like Megalodon had millions of years to respond to gradual cooling and isolation. Today's large animals face rapid shifts in temperature, chemistry, and prey availability compressed into centuries or less. The system's ability to buffer change is being tested again, but without the luxury of time. Understanding the echoes of ancient giants reframes how we see modern southern oceans. They are not fragile wastelands at the edge of habitability. They are highly specialised systems operating under extreme constraint, still capable of supporting immense life when conditions align. Their history explains both their power and their vulnerability. When whales surface in polar seas, when predators coordinate hunts in frigid water, when productivity explodes along a shifting ice edge, these are not novelties. They are reminders. The ocean has done this before, on a much grander scale. What we see now is not the beginning of something new, but the remainder of something old. And as the story continues, these echoes become increasingly important, because they invite a deeper question. If the ocean once supported giants, and still carries the machinery that made them possible, what does that tell us about scale itself, about survival, and about the lessons Antarctica continues to offer from beneath its icebound surface? Antarctica has a way of stripping ideas down to their essentials. It does this quietly, without spectacle, by removing comfort and excess until only what truly matters remains. In that sense, it has always been a teacher, even when it was warm, even when its seas were crowded with life. The lessons it offers are not about ice alone, but about scale, about endurance, and about how survival is shaped not by strength in isolation, but by alignment with systems far larger than any single organism. One of the clearest lessons Antarctica offers is that scale is never absolute. What seems enormous in one context can become fragile in another. Megalodon was not too big in a world that fed it. Its size was appropriate, even efficient, within a system that rewarded reach, patience, and dominance over distance. When that system changed, the same size became a liability. This does not mean size was a mistake. It means size is always conditional. Antarctica teaches this again and again. Its modern ecosystems are dominated by organisms that make sense only in that specific context. Krill are small, but they exist in numbers so vast that their collective biomass rivals that of much larger animals elsewhere. Whales are enormous, but they survive by filtering the smallest prey imaginable. Seabirds travel thousands of kilometres for a single feeding season. Seals dive to extreme depths repeatedly. None of these strategies would work everywhere. They work here because the system demands them. Scale, in this sense, is not about being large or small. It is about matching the rhythm and structure of the environment. Ancient Antarctica matched giants. Modern Antarctica matches specialists. both are expressions of the same principle. Another lesson lies in survival itself. Survival is often framed as resistance, as the ability to endure hardship unchanged. But Antarctica shows that survival is more often about transformation. The continent has survived by changing its role in the global system. When it was warm, it distributed energy broadly. When it cooled, it became a driver of circulation and climate regulation. It did not cling to one identity. It adapted at the scale of continents and oceans. The organisms that persist around Antarctica follow the same rule. They are not survivors because they are stubborn. They are survivors because they are responsive. They time their lives to pulses of abundance. They move when movement is required. They store energy when storage matters more than speed. They accept long periods of scarcity in exchange for brief periods of excess. This pattern mirrors the ancient past more than it might seem. From this perspective, the disappearance of giants like Megalodon is not a story of failure. It is a story of misalignment. The environment changed what it rewarded. Traits that once conferred survival stopped doing so. New traits rose in importance. Evolution responded accordingly. Antarctica did not reject giants out of hostility. It simply stopped offering the conditions they required. There is also a lesson here about limits. Antarctica shows that limits are not fixed boundaries. They are thresholds shaped by interaction. The same ocean that once fed the impossible later constrained it. The same currents that once connected hemispheres later isolated them. Limits emerge from relationships, not from absolutes. This is especially relevant when thinking about modern change. We often ask whether systems can support certain scales of life, industry, or consumption, as if there were simple yes or no answers. Antarctica suggests the real question is not whether something is possible, but under what conditions it remains viable and how quickly those conditions can shift. Another quiet lesson Antarctica offers is patience. Geological and ecological change there unfolded over millions of years. Species had time to respond. Systems had time to reorganize. Even so, not everything survived. Today, changes are happening, orders of magnitude faster. The lesson is not that changes are natural, but that speed matters. Alignment requires time. Antarctica also teaches humility about prediction. If we had stood on its shores during a warm era, watching giant predators move through blue waters, it would have been difficult to imagine the frozen desert it would become. If we stand on its ice today, it is equally difficult to imagine forests, rivers, and rich coastal seas. Yet both states are real. Both existed. The planet does not privilege our present moment as definitive. There is a lesson here about perspective. When we judge survival strategies, we often do so from a narrow window of time. Antarctica stretches that window. It reminds us that what looks optimal now may not remain so, and what looks extreme or unnecessary may once have been perfectly suited to a different world. Perhaps the most subtle lesson Antarctica offers is about integration. Nothing there exists in isolation. Ice affects currents. Currents affect climate. Climate affects life. Life in turn influences chemistry, circulation, and energy flow. Giants did not exist because they were powerful alone. They existed because they were integrated into systems that could carry their weight. When those systems shifted, integration broke down. Size lost its context. Survival required a different fit. Antarctica shows that no trait, no matter how impressive, guarantees persistence if the system that supports it changes. And yet, there is no sense of loss in the ocean itself. The disappearance of giants did not leave a wound. It left space. That space was filled by new forms, new strategies, new balances. The ocean continued to function, to circulate, to produce life. Survival at the system level is not about preserving specific outcomes. It is about maintaining flow. In this way, Antarctica still teaches us about survival, not as a competition between winners and losers, but as a continuous negotiation between life and environment. Scale, rises and falls. Strategies emerge and fade. What persists is the relationship itself. As the story approaches its final movement, this perspective becomes essential. The question is no longer simply how giants once lived, or why they disappeared, but what their story reveals about the nature of change, about the conditions that allow extremes to exist, and about the quiet ways the planet signals when those conditions are shifting. Antarctica does not speak loudly. It does not announce its lessons. It reveals them slowly, through absence as much as presence, through what it no longer supports as much as what it does. And in listening to those lessons, we begin to see that the story of ancient giants is not separate from the story of modern survival. It is part of the same continuum, written in different climates, under different skies, by the same moving sea. As the ocean settles back into itself, it leaves behind no monuments. There are no markers rising from the seafloor to announce what once moved through these waters. No outlines etched into the currents to show where giants passed, where immense bodies displaced water and shadowed entire food webs. What remains instead is quieter than absence. It is memory carried by structure, by pattern, by behaviours that still make sense only when viewed against a deeper past. The colossal sea that once surrounded Antarctica is gone, but it is not erased. It lingers in how energy still concentrates along certain boundaries, in how life still gathers where movement and nutrients align. It lingers in the fact that even now, in one of the coldest oceans on Earth, the planet continues to produce abundance at a scale that surprises us, not evenly, not gently, but decisively when conditions allow. When we talk about Megalodon, or about any ancient giant, it is tempting to frame the story as one of loss, something magnificent that vanished, a peak that the world no longer reaches. But the ocean does not experience history that way. It does not mourn. It repurposes. It reallocates energy. It reshapes pathways. The disappearance of a giant is not a collapse. It is a rebalancing. The quiet memory of that colossal sea lives on in the fact that Antarctica still matters so profoundly to the planet. Its waters regulate climate. Its currents drive global circulation. Its seasonal rhythms still dictate when and where life flourishes across half the globe. These are not the traits of a marginal place. They are the traits of a system that has always operated at scale, even when that scale takes different forms. There is something grounding in realizing that the largest predators Earth has ever known were not accidents or anomalies. They were expressions of a world that could afford them. Their rise tells us about abundance. Their fall tells us about constraint. Neither tells us that the ocean has diminished in importance, only that it has changed how it spends its energy. If you could strip away the ice today, not suddenly, not catastrophically, but gradually, over millions of years as it once did, the ocean would not hesitate. Currents would reconnect, shelves would reappear, productivity would spread outward. The machinery that once fed giants would begin to hum again. Not because the past is waiting to return, but because the rules have never changed. Energy flows where it can. Life follows. That is perhaps the most enduring memory of all. The ocean is not nostalgic. It does not repeat itself out of sentiment. But it does reuse successful patterns when conditions allow. Size, abundance, and dominance are not relics. They are options, always available, always conditional. And so the story of Megalodon in ancient Antarctic seas is not really about shark, it is about context. It is about what happens when warmth, motion, nutrients and time align. It is about how ecosystems behave when they are allowed to stretch without immediate penalty. It is about how survival looks when the world is generous, and how it changes when that generosity narrows. In a way, the quiet memory of that colossal sea invites us to think differently about our own moment. We live during a time of rapid change, when systems are being pushed far faster than they were in the deep past. The giants of today, whether biological or otherwise, are navigating a world whose rules are shifting quickly. Antarctica reminds us that scale is not permanent, and neither is dominance. What matters is fit. What matters is timing. What matters is whether the systems we rely on can still carry the weight we place upon them. The ancient southern oceans carried immense weight. They did so for a long time. When they could no longer do so, they changed course without drama. The sea did not break. It adjusted. There is a certain calm in that realization. It suggests that the planet is not fragile in the way we often imagine. It is resilient, but not accommodating without limit. It supports extremes when conditions align, and it withdraws that support when they do not. There is no moral judgment in this, only process, and perhaps that is why the memory feels quiet rather than tragic. The giants are gone, but the ocean remains deeply capable. It still produces awe, it still surprises, it still reminds us that emptiness is often an illusion, and that absence can be as informative as presence. As you sit with that thought, wherever you happen to be listening from, whatever time it happens to be in your part of the world, the ocean continues its slow work. Currents move, ice shifts, life gathers where it can. Somewhere far south, beneath dark water or midnight sun, the sea is still doing what it has always done, responding to conditions, redistributing energy, carrying forward the memory of what once was without needing to recreate it exactly. And if this journey through deep time and colder seas has offered you a sense of calm, or curiosity, or simply a quieter pace to end your day, you're always welcome to share that feeling with others. A like, a subscription, a small signal that this space of slow science is worth returning to. Not urgently, not loudly, just as a place to drift back to when the world feels a little too fast. For now, there is nothing left to chase. The story does not end so much as it settles, like sediment drifting down through still water. The colossal sea is no longer here, but its memory remains woven into the ocean we have today, patient, vast, and quietly alive.